Hello, this is the third type of root finding method, lecture 7, polynomial methods for root finding. So the first we studied about bracketing method. We given a bracket and we should know the root should be within the upper and lower limit of the bracket. The second type of root finding is the open method, where we just start with an initial guess and then work towards the root. Now here we will talk about two different types of method, and you will see that the approach is a little bit more intense in terms of details than the other two methods. But my goal is here to explain this method, and you need to understand it, and then there's nothing to remember. We will do some examples, and then the main goal is to have a good understanding of how this method works. Here is a graphical explanation of the Mueller's method. The first one on the left, this is called the scant method, which I did not cover here, but I will quickly explain what this is. So that's you start with two initial points, the initial guesses. So one initial guess is x1, the other initial guess is x2. So we can find the function, the function value at x1, x2, because we know the function. So using these, we can fit a straight line through these 2 points, and then we can find out where that straight line intersects the x-axis. So that is an estimate of the root. The Mueller's method is, instead of fitting a straight line, we will start with 3 initial guesses. So if you have 3 initial guesses, you can fit a parabola through them. So that's a parabola. So you fit a parabola through them and then find out where that parabola intersects x-axis. So that is the estimate of the root. But you should know, since it is a parabola, it will also intersect x-axis there. So we don't want that. We will select only this one that is closest to the initial guess. So how to do that and how to iterate this, all of that is taken care of in this method. It was all derived, and it comes to a procedure. We have to just follow the procedure, knowing that essentially following that procedure will do just this. So we will start with 3 initial guesses, find the point that intersects the x-axis, and then use that point as one of the 3 guesses. So we will get rid of one of these 3 and use the new one as the new 3 points, and then keep on iterating. So that is the explanation for how Mueller's method works. But the remaining is just a procedure, which I'm going to explain. Also, in the lecture notes, it gives some fairly good amount of proof of how it's all done. So that's what I'm going to spend some time explaining. What is the basics and how it works. Then it is the procedure and the algorithm. I'll also explain that. Okay, so here's an algorithm that implements Miller's method. So you will see that the input, usually we would expect input of the algorithm, the initial points, x0 and x1, x2, that is we needed, but using xr and h, it is computed here. So xr is x2, x1 is x1 plus h times xr, x0 is xr minus h times xr. It is initial guess. So initial guess, it doesn't need to be in that fashion. These are initial guess equi-spaced. So that's, it doesn't need to be, but that is how this algorithm assumes. As I said, this is a numerical method. You can just give three different x0, x1, h2, and you can rewrite this, or you can try this in programming, different ways to initialize it. So it is, end of the day, initial guess. And then we'll do a while loop, which is, I use different approaches to indicate a while loop. But this is from the book. So that's a while loop. The while loop breaks. So that is when the while loop will break. The while loop breaks if this condition is, if the condition is satisfied. That is, if the number of iterations is greater than the max iter, or this we are close to the required accuracy, then the while loop exit. And then so, except for the while loop, then this is exactly as it is explained earlier in the lecture notes, how we will compute these A, B, and C, and use that to find the first XR. And then we will select one of that, and then we will print the root. Okay, one second. Where is the print root command? I have missed it. I will be back. Alright, so I made a small change there to print iteration. Also, there was a typo that was fixed here. So once you, so that's the new root. So once you have the new, that is XR, once you have it, the algorithm is written. In C++ or in other program, we will just write the command for display that way. Every time you have a root, you can just display it. So then you will just so here the circular approach is used. So this is the one that was corresponding to the second approach here, complex method. But you can always change this algorithm just for real root. So this one assumes complex root. And so that's it. That's algorithm for Miller's method. In this example, one iteration is given all the numbers. If you just give this example in the algorithm, the best way is to program this algorithm and give this, and then you will see this. And so if you do that, these are the different iteration. That is what you will see for XR. Alright, so that's basically it for the Miller's method. Now we move on to another polynomial method for root finding. Alright, so I'm not, this time I'm not going to go into deep the Bayes-Stokes method, but this is something I want to include at least as an introduction, and to say that there is a method such as Bayes-Stokes method, and we just discuss an overall how it works. So the Bayes-Stokes method works in a polynomial diffusion approach. You take a polynomial and then you find the root of this polynomial. That is the goal. So if you can divide this polynomial by x minus t, and there is no reminder, then it is one of the rules. So it starts with that principle and it goes a little bit deep. So this time, I'm not going to go deep and explain this. I also need to include the algorithm for that, which I haven't. So I thought you can just maybe read about it and have an idea about Bayes-Stokes method. Other than that, I won't be spending too much time on this. Just knowing this approach, maybe reading about it a little bit in the book, I would suggest to get a better idea of how it works. So you can just ignore this this time. So the details, so not covered this time. I suggest just reading it maybe here and also in the textbook for more information. So I will again I will the polynomial method for root finding is a little bit complex to memorize, but I will add Mollo's method is, if you see, I mean, fairly fairly straightforward, even though it's not that much. It involves a lot of steps. I will have maybe one or two homeworks, maybe one or two homeworks for Miller's method, and just skip Bayes-Stokes method. And as for even the exams, you will only focus about Miller's method, but all the exams are take home. So once again, there's no need to memorize anything here. Just understanding Miller's method will work. So for this one, so that's the end of. So I will add some. I will add some questions and then update it. Maybe one or two questions on Miller's method. So that's a summary of root finding. So we studied about bracketing method, open method, and polynomial methods. We studied two approaches each, even though in the polynomial method I only spoke about the second approach. I didn't really go into details. You can just read it about. I would suggest textbook because my note is not really complete for your information. But as exam is concerned, I will only consider Muller's method. That's only for take-home exams. Okay, so that's all for root finding. From next, after you return from reading week, we will go into other things. So that's all for root finding. Maybe other types of numerical methods about Splex method, optimizations, solving equations, linear algebraic equations, alternate differential equations, integration, numerical differentiation, things like that. Okay, so that's it for at least for the section before the midterm. I will post an announcement about what is covered in the midterm and how to prepare for it. All right, thank you.